In the last video, we looked into the PCA as a dimension reduction tool that is based on a linear transformation of correlated features, such as returns of all stocks in the index into uncorrelated features. We also looked at the PCA as a data visualization tool by projecting all historical stock returns onto a two-dimensional plane formed by the first two principal components. We did not find much insights in this graph, though. Let's take another look at it again. In that exercise, we colored points from different historical regimes by different colors. Green points here correspond to the period of 2001-2002, which corresponds to the dot-com bubble in the technology sector. Red dots correspond to the period of 2007 to 2009, where a credit crisis has morphed into a general economic crisis. The blue points are the rest of the observations, which we call here a benign regime. For this data, the PCA relies on a linear transformation of data, alongside with a truncation of less important dimensions to arrive at the graph shown here. One thing that stands out in this graph is that most points are located at the center of the graph. This is called the crowding problem. As you can see, the crowding problem seems to be a real problem indeed, and apparently not much can be learned just by looking at such two-dimensional view of the data. An interesting question, though, is what causes the crowding problem. It turns out that there is a different non-linear way of two-dimensional data visualization which often works much better than the PCA. This method is known as the tSNE, which stands for the T-distributed stochastic neighbor embedding. The tSNE method was proposed in 2008 by Vander Marten and Jeff Hinton, and since then has become a very popular tool in machine learning and data science. Now, how does the tSNE compare with the PCA? There are multiple dimensions by which we can compare these two methods. Let's start with the type of optimization algorithm used by both methods. While the PCA is a deterministic algorithm, the tSNE is stochastic. One consequence of this is that the PCA leads to a unique solution, but the tSNE may lead to different results for multiple runs on the same data. Furthermore, while the PCA is a global method, that is, all n-dimensional points affect a given two-dimensional projection point, the tSNE is a local method, which is with an induced global behavior. The two methods also differ in how they handle extra dimensions. The PCA simply truncates all other principal components when projecting onto a 2D plane. But the tSNE does not discard extra dimensions. Instead, they impact the position of a projection onto the 2D plane. Finally, the last major difference between the two methods deals with interpretability. While the PCA is straightforward to interpret, it's just the rotation of coordinates, the results of the tSNE are sometimes not easy to interpret, as we will see shortly. Now let's see how the tSNE works. The tSNE method is a probabilistic method based on matching two distributions. The first distribution is a distribution of data points in the original d-dimensional space. The second distribution is a distribution of projections of these points onto a 2D plane. Let's start with the first distribution. The tSNE assumes that all pairs of points xi and xj are generated by a Gaussian distribution Pij, which is a symmetrized version of a Gaussian density of xj centered at xi, with the data-specific variance sigma I squared, shown in this formula. We will discuss the choice of sigma I below. Next, let's discuss the distribution of projections of data points into a 2D plane. The method assumes that points on a 2D plane correspond to a student t distribution with 1 degree of freedom, which is also known as the Laplace distribution. This distribution has two interesting features. First, it has fat tails. That is, probabilities of large events are substantially larger there than for a Gaussian distribution. Second, large distances would be suppressed in this distribution as a power law. It turns out that these two features of the Laplace distribution help a lot for a better visualization with the tSNE method. Now, one remaining step is to choose the data-specific variance as sigma I squared. The tSNE fixes variance for each point xi such that the distribution of points xj around xi has a fixed perplexity. The perplexity of the distribution is simply 2 raised to the power of entropy of the distribution. As suggested by this formula, when we fix perplexity, we fix the number of neighbors that the point xi compares itself to. After variances are fixed for all points, the algorithm chooses optimal values of projections yi by minimizing the KL divergence between the original distribution and the distribution of projections. This objective function can be optimized using stochastic gradient descent with its gradient given by this simple expression. For your convenience, the complete algorithm is copied here from the original paper. All steps here should be already familiar to you except the very last line in the loop that uses the momentum term in optimization, which is the last term in this expression. We will talk about momentum when we discuss optimization methods in more length. But for now, let me finish this video by showing you results of the tSNE visualization of the same Dow Jones data that we used in our examples with the PCA. Let's take a few values of perplexity and draw the resulting projections. So if we take perplexity equal 10, we get this shape that vaguely resembles an octopus. But if we increase complexity to 50, we all of a sudden get something that looks like an anaconda. Let's increase complexity to 100, and now it looks like a dinosaur. Let's continue. Let's take it to be 500, and then we get a shark jaw. And finally, drums, please. We take complexity to 1,000, and what we get is the first ever visualization of the famous volatility smile known in option trading. Well, of course, it's a joke. It has nothing to do with volatility smile. It's just a nice visualization of the data. But it does look like a smile, and which perhaps we should see as a hint for us to stop increasing perplexity. So as you can see, what you get on this graph substantially varies with the amount of, with the value of the perplexity parameter, and often leaves lots of freedom for different interpretations. Further details on the tSNE method can be found in the original paper. I only want to add a few short comments here without going into much details. First, the basic algorithm is not well scalable, as it has a quadratic complexity. But using some special tree-based algorithms, complexity can be reduced to O of n times log n. Second, the basic tSNE algorithm is a data visualization tool, but not a dimension reduction tool. as it doesn't provide a trained representation of data that could be used to project new data points onto the plane. All new data points should be included again in the data set and retrained. So, to summarize, in this video you got familiar with the tSNE, one of the most popular tool for data visualization. This was our first nonlinear unsupervised learning method. And as I noted earlier, the tSNE in its basic form is mostly used as a data visualization tool rather than as a dimension reduction tool, as it does not provide you with a given learned representation that you could apply to a new data point once it's available. Instead, the whole algorithm should be run again. The basic tSNE algorithm also has issues with the computational complexity. That calls for some additional technical tricks if we want to apply it to large data sets. In the next video, we will take a first look at the autoencoder, another nonlinear dimension reduction method that is free of such deficiencies of the tSNE.